Here's the outline of today's talk. I will start with Newton's integration story. We know that Newton's principle of doing integration, but there is something missed by Newton. Newton missed something, which is very interesting. And then I will introduce a method named Genz-Malik rule to solve multiple integrals, means doing integration in high dimension. Then there are actually many methods to do this numerical integration. I will compare them. And beside these slides, I will show some C++ code to how to use this Genz-Malik rule. So I think we are familiar with Newton's integration because integration was invented by him or Leibniz. Informally speaking, consider a one-dimensional space from Newton. What Newton did is divide this interval from A to B into infinitely small intervals. Then compute the area of this interval by the sum of small rectangles. It means you times its height by its infinite small width. Then you estimate the error by left side approximation, compared it with the right side approximation. Then you consider then you divide this interval to infinitely small, so the left side and right side so the left side and right side are equal. Then it means the integral converges. This is a principle and informal idea behind Newton's integration. But what if we put it in more formal way? Is that still Newton we divide this interval into smaller intervals, but we approximate the function by a zero-order function, a zero-order polynomial, then estimate the error based on first-order derivatives. Still use the divide and conquer method. So the problem of Newton's idea, very primitive idea, is numerically inefficient. Though you can use some smart algorithm to compute the exponential polynomials. But what Newton observed is computing the area of these small rectangles is very efficient. It can be very quick. This means, put it more formally, is integrating polynomial is very simple. So why put it formally is what if we give up the idea to approximate the small intervals by linear kernels? We could use higher order polynomials. Put it, if we imagine more widely, higher order polynomials can be decomposed into orthogonal polynomials. And this is actually a spectral method to say we approximate each small intervals by map it into a generalized spectrum, and the spectrum is defined by orthogonal polynomial. This is a bit abstract, but if you imagine this map by Fourier transform, the Fourier kernel is exponential, but the kernel we use here can be follows the Lagrange polynomial or Hermite, Chebyshev, etc. The reason the reason people use different kernels because different orthogonal polynomial consider different boundary conditions. For example, if you go back to previous slides, you want to consider the closed side of this A to B, then you may need you may need orthogonal polynomial defined on closed sides. Or if you consider some infinite or infinitely the limit to 0, but on the open side, then you can use the kernel defined on the open side. The most interesting thing is this spectral method, as far as I see, is also observed by Newton, because in another area in optics, Newton uses prism experiment to decompose the light into different into different frequency. Yes, maybe using the orthogonal polynomial by an analogy of frequency, it can be much simpler. So maybe the question will be using the higher order polynomial, how to justify the use of higher order polynomial. Is this mathematical theorem named Weierstrass approximation theorem? It is to say that suppose an arbitrary continuous real valued function defined on real interval, then you can approximate this function to an arbitrary accuracy to use a polynomial. And then the computer can solve polynomial very, very efficiently, like a first year high school student. And with this approximation theorem, you can do it. So far, are there any questions? So the real challenge I faced is the challenge to do multiple integrals. It is like if you compute a numerical integral in one direction, you will need to compute the tensor product in higher dimension. Then you will face the curse of dimension. You got exponential complexity. In particular, if there is correlation among dimensions, it will be more challenging. But like the Weierstrass approximation theorem, it was extended by a mathematician named Stone to say this approximation can go beyond a one-dimensional closed interval for an arbitrary compact Hausdorff space. Means if you say the space is dense and separable, then you can do the same thing. You can use the same idea to do approximation by polynomials. So the word sub-abstract or the dense, it's very vague. I put it in a simpler word, is in our daily space, the Euclidean space, this Rn is Hausdorff. Then if you meet continuous real valued function by here we discuss the two-dimensional case by defined on a domain of rectangle, then there exists such a polynomial function of two variables. So you can do the approximation. You can do a very good approximation. The use of this theorem is to approximate a cube. Like in the right-hand side, this rectangle is two-dimensional cube by some samples. Here samples and compute the polynomial. The Genz-Malik rule is a seventh order approximation rule. Means you have a seventh order polynomial approximation of this high dimensional space. Then you use a fifth order approximation to estimate the error. It will be very efficient if you want to solve the numerical integration from 2 dimension to 7th dimension. Maybe this is the most efficient solver I've ever met during my research. In particular, you see, you compute the value of the points defined in the right figures. You can do it. You can compute their value parallelly. So in our case, we use multiple core processors and vectorized CPU to improve the efficiency. And this is critical if you have a much higher dimension to compute.
Guodong, excuse me, I'm not sure that I understood correctly. So to compute numerically the integral, you approximate the function by a polynomial.
Yes.
And to find the approximation polynomial, do you do some interpolation, for example, or how does it work exactly?
Yes, I will show it in the next few slides.
Okay, so, sorry.
Okay.
Go on.
So I start with the name and the big frame. The framework of this numerical integration is you define a cube and estimate the integral, like François said, by interpolation and approximation. They approximate a good interpolation. Then you estimate the error of this cube. If the accuracy of this cube is not, you're not happy with this, the accuracy, you divide this cube into a smaller cube and do the and repeat this function until it converges, like the Newton's integration rule in one-dimensional integration. So this is the question asked by François Duhon, is what is the integration rule and the seventh order integration rule? It is you have several roots. The root is here, the right hand side, the point you selected in this space. Then you do interpolation by monomials, which is a higher order counterpart of polynomials. So once you put this lambda 1, lambda 2, and into the higher order polynomial, you can actually compute the coefficient you need to do the interpolation. And this coefficient is invariant, and you can apply it to arbitrary numerical integration.
I'm not sure to follow. So there is a dimension.
Yes.
A dimension is n here, right?
Yeah, dimension is n here.
Then you have a collection of points, which are like the one you had in the cube, right?
Yes.
Which are, and these things are what the x, the lambdas, I'm not sure to follow them. Sorry to be slow. Could you just tell us what the notation is?
Okay. Oh, maybe I put the figure in the wrong. I put the figure in the wrong slide. So this lambda is the root you selected to compute the value of this function in the space you want to do integration. For example, the first kernel is this blue point in the middle, and then this lambda 2 is this right small rectangles, and this lambda 3 is this orange one, and lambda 4 this stars, and lambda 5 is purple triangles. So this is the root you use to approximate this the function, like by interpolation. Yeah, this is the interpolation point. Then then this Genz-Malik rule gives you that the W, the coefficient for this roots are invariant, given determined only by the number of dimensions. So you can develop a general solver. This is independent from the function you want to approximate or the function you want to do the integration. This is a general solver.
So just to be sure, so the BF is used as an approximation of F.
Yes.
No, sorry. Sorry. So BF. No, BF, sorry, is a value in the end.
Yes, BF is the 7th order approximated value.
Okay, so it's the approximation of the integral that you want to compute.
Yes.
So that is the first bullet point. And in the second bullet point, what happens?
What happens is you calculate the normalized case. Is you put this root lambda. I actually put it as x here is to say this x is a num variable. Then you do the integration, the real integration defined by the IF. Then you can compute the coefficient. Well, so if you consider a much simpler case, is like you consider Newton's case is y equals ax plus b, and you want to compute this a and b. That's a point here. You compute, yeah, that's a point given defined by this equation. I don't know if I make it clear. I think it's a bit abstract compared with Newton's first order approximation.
In fact, I just don't understand what IF is.
IF is the original function, the real function, and the BF is approximated function by polynomials.
Okay, and what do you mean when you say that we should put one x1 to the square, x1 to the fourth, and so on into this expression? I don't understand.
Okay, so yes, this will be a bit complex, and I put it at the end of the day, at the end of this slide. This means that you put this root into this integral and consider a normalized case of the integral. Okay. You can find this set of nonlinear equations and find the relationship between the root you define and the weight you expect. Here is a normalized function. The function is this function is this integral is you consider one in the space. It's not, how to say, normalized case compared with a general case.
So go on, François.
No, I was wondering, I mean, so you want to approximate the thing by a polynomial, and to use the polynomial approximation to compute the integral, right?
Yeah.
I was not, I'm not sure to see where the polynomials are in the earlier slides.
Yeah, the polynomial.
Right.
The polynomial is this guys.
Okay.
Yeah, this is the spectrum we want to map to.
Okay.
Okay.
Yeah.
Okay. Right. So and that's what you said. I mean, each polynomial is a monomial, right?
Yeah, monomial up
monomial.
to 7th order. It can be 7th order for one random variable or 3, which is 2. The sum is up to 7.
Sum is up to 7, and you look at all
Combination.
possible monomials with global degree 7, right?
Yes.
Okay, right. And so these are your okay. So these are your monomials.
Yeah.
And then you look at the combination of these monomials, which is a good approximation for the function. That's what you mean, right?
Yes. Yes.
Okay, I see.
And if I understand well, when you do that, you finally find that the value of the approximated integral is the one that you've written above with the W something and so on. That's it or not?
Yes. So the reason. So this is a general approximation. This is a kernel you want to use.
Yeah.
For a real function you want to compute, you just need this weight W and the lambda. I mean, this is
Okay, the lambdas and the x are sort of the same, right?
no, this x is a dumb version of the lambda.
Okay,
yeah,
so these are the monomials, right?
Yeah, it's
okay.
monomials.
And then you represent the, okay, so but the general aim is to represent the function by a linear combination of these monomials, right?
Yes.
And the weights are the way to encode this business, right?
Yes.
The W, right?
Yes.
Okay.
And there is a way to compile one into the other, right? And the choice and the main idea of this integration approximation is to use this class of monomials, right? That's the main thing, or other polynomials, because you only need to other classes, right?
Yeah, there are many possibility of different polynomials. So the idea here is you define, if put the word I can understand is you consider the Fourier transform. Here you define the spectrum, the frequency of the Fourier transform, and you have the weight attached to each frequency. Then you can use this Fourier transform to analyze all kinds of signal functions. So here is you define an analog of Fourier transform. You have your frequency is defined by the monomials, and the weight attached to these monomials. And you define this is a generalized Fourier transform. You can imagine it's in the space of yeah. So
okay, but the main point is that you produce a set of polynomials.
Yes.
Here there are monomials, and then you use the knowledge that you have the function sampled at some locations, right?
Yes. Yeah.
To see what is a reasonable set of coefficients in front of these monomials, and you have a sort of linear system of some kind. That's what you are needing to get the W's, right?
Yes, that's true.
Okay. So what I don't understand is why there are only 5 W's, because you have more. I mean, if you go up to polynomials of order monomials, all monomials with this coefficient, this global power less than 7.
Oh, this is due
There are
to
much more, right?
they're due to symmetry.
Sorry.
Symmetry.
Because your function. Why symmetry? I don't know.
The symmetry across different dimensions. You see the different points, right? Or these are symmetry across different dimensions. So they are invariant for each lambda here.
Yes, if I understand well, for example, for W2, you will do the sum of f of lambda 2 0 0 0 0, but also f of 0 lambda 2 0 0 0, and so on.
Yes, that's true. That's the permutation.
Yeah.
Across dimensions. And there are symmetry. You use the invariance. You can use one weight to denote this symmetric point.
Yeah.
But the function itself to be integrated is supposed to have symmetries or not?
No, the function, there is no function to be approximated. This is a unit function. You consider what we're doing here is to say there is a general function, just the polynomials without the real. So this is the basis of function space. You see.
Yeah, but your function f is given by external thing. The function is the function to be approximated, right?
Yeah, the function is you put this unit basis into the approximation system, and you got that. You can got this nonlinear system.
So, if I understood well, you consider the basis of all the polynomials you may encounter, and then you redefine some polynomial as a linear combination of this basis to get the result.
Yes, this is true. This means if you imagine we are working in the functional space, we are dealing with this unit function here, and this unit function so you can use this linear function to compute more general function, arbitrary function. So that's why it's a general solver.
You just calculate the things for this basis.
Yes, it's basis.
Just once, and then you will use the linear combination of them.
Yes, that's the idea of general solvers. Okay, so.
May I ask one clarifying question? Yeah. So this is approximating the output of the integral, not the function itself, not the function being integrating. So BF is an approximation of IF, which is the output of the integral, or the function f.
Yes, there are different levels of functions here. This f is the base of is the basis of all kinds of functions that you can map into this function space. Then how to clarify this as a basis rather than a real function, the realization of a function. Wow.
No, but the question is about whether the BF is a representation I mean, earlier in the first thing you said, well, I have this function, yes. I approximate it by a polynomial, and then I do the integration using the polynomial thing, right?
Yes.
So, and our question, if I get it correctly, was whether the BF was a polynomial representation or approximation of the function, or some way to compute the integral. Is it the value of the? Yeah. Is it the value? Is it a surrogate of IF or a surrogate of F? That was our question, if I get it correct.
Yes.
So so this BF is it's, in my understanding, they are accurate value of the they are accurate, they're not approximation. The value of the BF is you put the basis x1 square x1 power of 4 into this integrate this into this integral, then I'd rather say you put this 7 you put this 7 basis into the integral itself. You got the projection of this integral in this basis.
Okay, I see. Thank you.
Yeah. So yeah, this is yeah. Okay. Maybe I should if I use a simpler word in the word I can understand, is you have a high you have a it's actually an inner product between a function to its basis, and then you got the projection of this function into this basis, and the amplitude of a realizational function is a thing of interest for the solver to solve. But the solver itself considers the basis, the basis of this functional space you are interested in. Yeah. So the error estimation discards the 7th order, the highest order basis. Then you can estimate the error of this approximation by the difference of 5th order approximation, 7th order approximation, and say if it is not you are not satisfied with this accuracy, you can do a you can divide your cube into a smaller cube and do an approximation. The method to the strategy to divide is so I put it here. You compute the difference the difference in the axis named absolutely force difference. So this orange point in this direction and orange point in another direction. Then you find you compute the arrow and say if the arrow is large, you divide the cube in that direction. So actually, it's the algorithm is just made of these 3 steps. Estimate the integral by 7th order approximation, and then estimate the error by its 5th order approximation, and then divide the cube you are interested in into a smaller cube if the accuracy is not satisfied.
So what you call 5th and 7th is the total degree when you add up all the degrees of in this monomial.
Yes, the monomial basis.
Okay. And so the division of the cube or whatever, right, is to, well, if the function is fluctuating a lot in a region, you might want to make, if the function varies a lot, you will make smaller cubes.
Yes, you will make smaller cubes by cut it in a direction that changes fast. The fastest change.
Yeah, right.
So this algorithm is, in my opinion, the most efficient, and I will show you the efficiency by the use case, real use case. And there are other methods to compute higher order integration, numerical higher order integration. The one is Monte Carlo method, to say you define a function and then you randomly generate points in this direction and compute the value. Then the integration is the expected value of the point you generated, the value you generated. Compared with Monte Carlo method, I think the Genz-Malik method is more accurate and based on deterministic rules. In particular, in my case, it can address the singularity along the boundaries. You can define the behavior, how you approach your singular points. But Monte Carlo can hardly do it.
Just two questions here. The first one is that you say that I mean, avoid the cost of dimensionality. You still have to sample the random points in the Monte Carlo method, right? So, I mean, if you sample according to a Poisson or determinant point process, you still have to build points which are in high dimension, which is costly, right?
Yes.
So it partly avoids. The second question is about, I mean, so because you wanted smooth functions in this because of you want to approximate by polynomials and you want to use this approximation theorem that you alluded to, right? Well, the Monte Carlo method is not oblivious of this thing, right? So it's just the Monte Carlo method is some sort of you could have any I mean, the big integration ideas would work in the Monte Carlo method, whereas here you want to approximate polynomials, and so you need smooth functions of some kind in the first bit. So that's the difference, right?
Well, yes. I think the Lebesgue measure is beyond my understanding, but the idea for Genz-Malik is approximate a function by a smooth function. So you'd better expect the function itself is smooth rather than change rapidly. But the Monte Carlo method is based on, as you said, the Lebesgue integral idea. It's not based on approximation. So it doesn't require the condition of smoothness. Then the most straightforward comparison is compare this Genz-Malik method against the iterative method. Iterative method is do the integration along each dimension and subdivide and compute. In each dimension, each point you compute the integral in other dimensions iteratively. Then this method indeed is this exponential complexity. Means, for example, in the right-hand side, if you want to compute 5 points in each dimension, you need 25 points in total. But it will be easier to compute the kernels you want to exploit, like the one-dimensional case. But Genz-Malik method will require much less function evaluations.
But Guodong, it's still exponential, isn't it? Because if I remember well, the number of points to compute was something like blah blah to the power n, isn't it?
Yes, but that's the point I want to discuss here. Each cube requires 2 powers n plus 2. This is the highest order. This is also exponential, but you can subdivide this cube and only do. I mean, you don't have to sample across this dimension in the whole interval, but
yes,
yeah. So in practice, within each small cube, you have exponential complexity, but this is finite. But in iterative method, if along each dimension, you have to do almost infinite sampling. Then
it's not the same exponential. I agree.
Yes, yeah, this is not the same level of exponential. But I think maybe maybe simulation can speak louder than pure word. I will show you how it is used in C++. So the conclusion is the conclusion of this method is Newton starts the integration by first zero order and first order approximation, and then you can use a higher order polynomial to approximate the function within the interval of interest. And actually, this is this idea followed by Jacobi, followed by Gauss, named Gauss-Jacobi scheme. It received a success in one-dimensional case, but how to solve it in high dimension, namely multiple integral, are less known and less general. As far as I know, even in MATLAB or in C++, there are few this kind of solvers. In particular, in MATLAB still employs iterative method, namely you do integration iteratively. So maybe to justify its efficiency, I'd like to jump to here. So this is a very naive application of the Genz-Malik method. You see, I prepared two functions. They are smooth, but they are not. Actually, you can compute it analytically, but I do prefer to compute it by the efficient Genz-Malik method. So I do a test for the first function, which is y times 1 minus relay kernel. You see, in a cube, you only need 85 function evaluations. Means you only need to divide this cube twice, and you can achieve a super high accuracy up to eighth order.
Could you say well the function? I don't see the function. Sorry.
Yeah, the function is here. The others are helpers to. Right. So you have the function y times 1 minus 1 divided by 1 plus x. This is an arbitrary function. You can do arbitrary function.
So you're on dimension 2, and
yeah, in 2 dimensions.
And you want to evaluate the integral of this function in what region?
In the region of a cube defined from 0 to 1, 0 to 1. Yeah, but these are general. The solver are general. You can define the cube arbitrarily, and you can define the function arbitrarily. And you can define the accuracy you expect, and you can get your result very quickly. So if you want to tell, you want to say, you can say this is another function of interest, is exponential of the Gaussian kernels minus x squared minus y squared. So I save it and compile. You see, it's also very fast. You need about 400 function evaluations, and you can achieve the accuracy up to 7th order. Yeah, so.
How does the estimated error compare to the actual error?
The actual error will be much smaller than this estimated error. So because you consider smooth function, and just consider the Taylor expansion, the arrow term are at a higher order of this bound. This is a very pessimistic bound given here. So for example, you say it's 7th order arrow, but the real arrow can as small as 10 to 15th order.
Okay, thank you.
And so, okay, so it will be based. So you have two variables right here. So it's 2 dimensional. So you will have these polynomials of. And so, is there a way to see what the polynomials are in this case, or you compute the coefficient just to see?
Yes. So behind the screen is you define the root, the lambdas, and you define this weight and the weight of arrows. Then you do this parallel computation very fast and get the results. Yeah. So yeah, this is 2D case. There are 3D case, 4D case, or are very efficient. Well, and so this is I may end the talk here.
And so, if you would, so I mean, I'm aware of there is lots of work on this Monte Carlo method of using determinant of processes. So lots of results. So I mean, how does it compare to the? Where is the range where it's better than the Monte Carlo? I understand that the Monte Carlo is by definition I mean you have a random error right here, but so I mean when should you use the Monte Carlo? When should you use this type of methods? Depending on the number of the level of integration, how many integrals? What would be the guideline on what to use in what cases?
Yeah, I didn't do experiment by myself, but I read in the paper in the literature say using this method up to 10 dimension. When it's beyond 10 dimension, it may be not efficient to use this Genz-Malik method.
I see. So really, the Monte Carlo is for very high dimension, and this is for up to
reasonable dimension.
reasonable dimension.
Yes. Yeah.
And okay, and what is the reason for which it starts failing in higher dimension?
It's also the complexity. It's like
Yeah, the 2 to the n story. Right?
Yeah, the 2 to n story. In 10, imagine the 10 dimension, you have to evaluate each cube 1,000 points each cube. Then it's maybe a waste of time. But a high dimensional cube, not this 2-dimensional cube.